Hi there, welcome to today's video. In this particular video, we're gonna go through the enthalpy calculation. So looking at just Q equals mc delta T, because I have already done the Hess's law calculation previously in one of my videos. You can check that out. And also I'm gonna talk a little bit more about entropy. So like always, this is more specifically looking at these two concepts. And if you want to look at more questions, I strongly recommend you to do some of the older exams, and I've covered the past 3 years of examination papers, so you can practice more. Because for those videos I do tend to go through them a little bit quickly, so hopefully this one I can slow down and just be a little bit more specific and go through this particular two concepts. Okay, so let's get started. So whenever you see a diagram like this, and whenever you see before reading the question, when you see this 4.18 joules per degree Celsius per grams, this is your typical MC delta T question. So this is where you need to use Q equals MC delta T, like without even looking at the question, because this the number I just highlighted is pretty much just the specific heat capacity of water. Now, just to put it into context, like what does this actually mean? So that 4.18, excuse the fireworks, guy fawkes here. So with the 4.18 joules per degree Celsius per gram, it just means if I were to heat up 1 gram of water to increase the temperature by 1 degree Celsius, that's going to require 4.18 joules of energy. So if you look at this, we're trying to determine the liquid methanol's heat enthalpy of combustion. If we put 2.5, if we use 2.56 grams of the methanol, which is in this burner, if we burn that much, the temperature, which is 500 grams, increases from 21.2 degrees to 34.5 degrees. And then we got given the C, and we know the molar mass. And I've mentioned this multiple times in my previous videos, is that the numbers that we give you in chem, you normally need to use them. You need to use them once and once only, and you don't need to use them more than once. Okay, but you have to use all of them. So let's have a look at these. So Q stands for how much energy that's making this happen. Like, say for example, if I want to burn this methanol to heat up the water inside this flask, if I burn the methanol, that's going to release energy. Then that goes, where does it go? It goes into water. Then that increases temperature. I know how much energy there is. The requirement is to require 1 grams per 1 degree Celsius, which is 4.18, and then I use this equation to give my answer. So the Q is how much energy is required to make this process happen. M is the mass of water. Now, sometimes they don't give you water. This could just be anything that has a lot of water in it. Okay, so in this case, it's just water. And remember, 1 gram is equivalent to 1 mil. Roughly the same. And C is just 4.18. And then change of temperature is you using your final temperature minus initial temperature. Okay. So Q equals mc delta T. So if we were to look at this particular question, I'm just going to go Q equals mass. That's the mass of water that we're looking at, which is 500 grams. We got that already. 500 times C, which is 4.18, and then times by the temperature change, which is 34.5 minus 21.2. Okay, because I started at 21.2, we didn't finish at 34.5, and that's going to give us a number. Where's my calculator? This is going to give us a if I apply all of them together, that's going to give us 27797 joules of energy. Remember, when we're doing enthalpy calculation to find out the delta C, we don't use joules, we use kilojoules. So this is going to be 27.797 kilojoules, and if I round it to 3 significant figures, which is going to be 27.8 kilojoules of energy. Okay, so much chemistry going outside with all the fireworks. So there you go. That's how much energy that we're dealing with. Now, once you find out how much energy, so this much energy is required, this 27.8 kilojoules of energy is required to heat up that 500 grams of water, increases by what, 13.3 degrees Celsius, which is 34.5 minus 21.2. This is how much energy that we need to do this. Okay, so you could burn anything. You could burn paper, you could burn fuel, you could burn coal. It doesn't matter what you burn. If I had 500 grams of water, if I want to increase the temperature by this much, I need to use this much energy regardless of what you're trying to burn. Okay, so if we're trying to look at this particular question, we're looking at the enthalpy of combustion. So this is where you need to understand that enthalpy of combustion, the enthalpy change, is used by negative Q divided by how many moles of the chemical that I'm actually using to make this happen. Because regardless of what I use, I need 27.8 kilojoules to raise this much water's temperature by this much. So the negative Q is just going to, so we need to figure out the mole. So this is the mole, this is the number of the mole of the chemical that we actually burned to release this much energy. And then N equals small m divided by big M, which is, and then you can go back here. This is where people get confused, because you got 2 grams and then people are like, oh, I got 2 grams, which one do I use? And just remember, you already use water, you don't need to use that anymore. So we're dealing, look at the molar mass. They don't give you the molar mass for nothing, remember? So you got the methanol, that's 32 grams per mole, and you got 2.56 grams on top, and that's going to give you 0.08 moles. Okay, so we got that. Now let's just substitute every number is in here. So that's going to be negative 27.8 kilojoules divided by 0.08 moles, which is going to be negative 347 kilojoules per mole. So that means you release 347 kilojoules per mole of methanol that you burn. Now, it's a very, 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 to me, like, because I'm quite competent with mathematics, and this is not very difficult. Okay, so it's very typical. You can find a question like this in every single year's exam, pretty much, but there are some variations. What are some of the variations? Is this? It's gotten, to be honest, the difficulty when they give you questions like that in terms of variations, the chemistry is not difficult, it's mathematics that is difficult. So here's what they can do, and I've seen them doing this before. They give you this, they give you delta H, they go, oh, here's the enthalpy of combustion. They told you the grams, like say, I'm just going to highlight everything they give you. Yeah, let's say if, for example, they give you this, they give you this, they give you the delta H, so you can figure out the Q, yeah? And they give you the 500 grams, and then they give you the initial temperature, and then they ask you what the final temperature is. So you just work backwards. Okay, so that's more like, all right, so you go, okay, so I know my delta H, that means I know my mole, because you can use the small m divided by the big M, so you can find out Q. Once you figure out Q, you know this number multiplied by this number multiplied this difference is going to equal to Q, so you have to solve X, like say you make that X. So it's more of a, it's not so much chemistry in terms of difficulty being increased, it's mathematics. You just have to learn how to do that. That's just math. That's, you might hit this like, why is that even difficult? It's just working backwards. One's working forward, one's working backwards. So it's more about just understanding what you're trying to calculate. You need to look at every single one of these numbers, and you know why we are using them. Okay, because once you understood that, then everything is going to be a piece of cake. Okay, so let's look at the next part. And again, this is very, very typical. Explain why this experimental value is much more smaller, which is always the case, compared to the numbers that we do, the standard theoretical number. Because first thing first, you have heat loss. Okay, so if you look at this environment, if you look at this equipment setup, it's very, very poor in terms of keeping the heat. You are going to lose heat to the surrounding environment, and that's just, heat loss, poor insulation. You can think of the things like this. You can say the container has no lid, that means you lose a bit of heat. You can say that there's incomplete combustion. You can say the conditions not standard. There are quite a few different ones. Again, grind some exam papers to see the variation, but that's pretty much the same. Okay, if you look at number 3 now, number 3, so this is pretty much I'll do with the calculation. So if you want to see more of these type of calculations, have a look at my other videos in terms of the examination papers and just have a look at that. But it's not really hard. Like I said, the Q, you just remember Q equals mc delta T, Q equals mc delta T, and then the enthalpy change is negative Q divided by the mole. Mole equals small m divided by big M. These are the only 3 equations you're going to need for this one, and you just need to know which number to substitute into which equation, which is, you know, kind of the difficult part. And like I said, sometimes they don't go forward. They don't go forward. They don't go, oh, here's M, here's S, here's C, here's T, figure out Q. Oh, you figure out Q. Here's a mass, here's a molar mass, figure out N, then figure out delta H. That is the most user-friendly version. And if you got that in the exams, I'll be laughing. But then sometimes they, you know, make it a little bit annoying. They, like say, they give you this. Like I mentioned before, they give you this, and they go, oh, what is that? And then you have to work backwards. Okay, so write down the equations, work backwards if you have to. Now, next part, we're going to look at the entropy change. So I'm just going to do this on here because the big part of entropy I'll explain later. So this is the enthalpy of, the entropy change going from liquid to gas. Explain the entropy change of the system and surrounding for the evaporation of methanol. So we know this is you going from methanol liquid to ethanol methanol gas. Now, there are 2 things we need to look at. One is looking at the system. The system is kind of like what's inside the reaction, like inside the container. Like if you do a chemical reaction, you're doing a test tube, in a beaker, in a flask, in whatever, this is inside the system. Then we look at the surrounding, which is the outside. This, like say, if you were to touch the outside of a test tube, you are technically looking at the outside of the system, okay, because you didn't put your finger into the solution, okay. So we need to look at 2 things. And we figured out this equation, this enthalpy change is negative 347, because we no, it's not negative 347, that's enthalpy of combustion. We did a different calculation. So you're going from liquid to gas, and you know, to go from liquid to gas, this reaction is going to be endothermic, okay, because you have to do bonds breaking. All right, so how do we determine the entropy change? So let's look at the system. So the system, you look at the states. You went from 1 moles of liquid to 1 moles of gas. So that means, you know, the entropy, the delta S inside the system is going to be positive. This is going to be positive. Okay, so the entropy increases because you have more gas particles. You made the entropy change. Oops, can't write. Is increases. Oh man, I can't spell tonight. Increases. Okay, because you're going from 1 mole of liquid to 1 mole gas, so there's more randomness, there's more disorder. Therefore, inside the system, the entropy increases because gas particles have a more random arrangement compared to liquids. Okay, now if you look at the surrounding is when this reaction takes place, there's always going to be an enthalpy change. In this case, the enthalpy change is positive. So that means when this reaction takes place, it sucks energy into the container, which makes the surrounding particles colder because it lost energy. So as a result, you know, this is endothermic reaction. Endothermic, that means energy is absorbed. Energy is absorbed. And where do they absorb it from? That is absorbed from the environment, from the neighboring, from the particles. You know, from the particles, absorbed from the surrounding. That's why we say surrounding. So if that energy is absorbed from the surrounding, so that means they will move. They'll move around less. so they are less random. Okay, because they have less energy. I mean, how many times have we done race reaction year 11, year 12? It's more energy, increase the temperature. What does that do in terms of race reaction? Oh, because there's more heat, they have more kinetic energy, they move around, they climb more of these solutions have more sufficient amount of energy to sort of blah, 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 blah. You did that in last year in year 11. So what if we talk about the opposite? You absorb the energy, so the particles are less random, so the surrounding entropy actually decreases. Okay, and when do we have a spontaneous reaction? Is when the total change of entropy, which are the two things I just highlighted, when these two entropy added together is positive. When that entropy, when this guy and this guy add together, if the number is positive, yay, you have a spontaneous reaction. If it's negative, nay, you have a non-spontaneous reaction. So this is to do when we say consider the entropy of the system and the surrounding, is more of a, you need to look at the inside the system, look at the chemical reaction. Do I have a change, increase of entropy or decrease of entropy? And then you look at the surrounding. Do I lose heat or do I absorb heat? Then figure out that entropy change. Then combine the two together. If they're both positive, like say there's a few scenarios here. If they're both positive, like say positive plus positive, obviously you're gonna have a spontaneous reaction. If you have a negative and negative, and if you add these two together, you're never going to have a spontaneous reaction. And what if you have scenarios like this? One is positive, one is negative. Well, it depends. If this thing that I've highlighted right now, if this change of entropy is really, really significant compared to this negative change of entropy, then it is spontaneous. Okay, so it just depends on which one is more significant, and you're not going to need to know that. We will say, oh, this reaction is spontaneous. How does that reaction spontaneous? Even though this happens, you can just use a clue that we give you to figure it out. Okay, so here's another example. So this is explain why liquid hydrogen readily burns in oxygen. So readily, so remember, readily burns means spontaneous. So they already gave you the answer. They're saying that why is it spontaneous? Okay, so they say consider both enthalpy and entropy changes. So let's look at the system. Let's look at the system, which is inside this chemical rate equation right here. You're going from 1 mole of liquid plus 1 mole of gas to 1 mole of gas and 2 moles of gas. So you're going from, obviously, the change of entropy is going to be positive. Why? Because you have more gas particles produced in the product side. So that means, more random disorder, blah, 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 blah. And therefore you have a higher change of entropy. Let's look at the surroundings. So the surrounding, you don't need to look at the system anymore, you look at this number. This is an this is an exothermic reaction. Negative, this means it's an exothermic reaction. What does that mean? That means energy is released. Energy is released. And where does that go? That means the surrounding particles that's on the atmosphere that's surrounding this thing, the surrounding particles become more random. They become more random because there's more heat. Okay, they become more random, therefore the change of entropy increases. So let's look at the entropy of the system. This is positive. Entropy of surrounding, this is positive, positive, positive. It's always going to be spontaneous, and therefore it's spontaneously combust. Nice and easy. Okay, so this is how you tackle questions like this. I think there's one more that we're going to do. Yes, there's one more. Now explain why sublimation of iodine is spontaneous even though the enthalpy of sublimation is a positive value. So sublimation is when you're going from you're going from solid into a gas. So again, whenever you do questions like this, think about the system, think about the surrounding. So they told you, let's look at the system. So you got, this is obviously positive because you're going from, why? Because you're going from 1 mole of solid to 1 mole of gas, and they're more random, blah, 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 blah. Let's look at the surrounding. They told us this enthalpy is positive. So that means energy is absorbed, and then you can look back up to some of the the previous examples, and we figured out that the entropy change is going to be negative. And they go, all right, so why is this why is this reaction spontaneous? Well, because this is more significant. Okay, so in terms of, because for this reaction to be spontaneous, this particular change of entropy inside the system must be more significant compared to the negative change of entropy of the surrounding. Therefore, it is spontaneous, and then you can get your full grade here. Okay, so this is how you do spontaneity in terms of entropy. So because a lot of people ask me that, because this is kind of new, well, not that new anymore, but and a lot of my students get confused with this, so I thought I'll do it for them, and then I thought might as well do it for everyone. But yeah, so here it is. This should cover everything. Hope you guys do well in the upcoming examinations and everything. And if you have any messages, feel free to leave a comments, and I'll respond to those. All right, guys. Thank you, and take care. I'll see you guys next time. Bye bye.